Hi everyone, my name is Elliot McDonald, and today I'll be walking you through the AMPL Tutorial 1. Cheminformatics data comes in many different forms, and in order to format this data in a way that is digestible to our machine learning algorithms, we need to curate the data. First, we're going to do an overview of how we do this curation process, and then we'll open up the code and do it ourselves. AMPL provides 5 custom functions to make cleaning your chemical data as easy as possible. These will allow us to take a raw dataset, standardize its smiles, standardize our output values, remove our outliers, and combine multiple values for the same compound. Let's take an example here where we have our raw, uncurated data comprised of chemical structure strings called smiles. We have relations or sensors. We have some value for us to predict, in this case the inhibition constants, and then the units for these values. Note that an equal sign or a blank in this relation column means the chemical has a Ki of exactly this value. But if there is a less than sign, it means the actual value is less than the lowest value tested for this compound, also known as left-censored. Likewise, if the actual value is greater than the highest value we tested, we see a greater than sign, and it's called right-censored data. For example, the second to last row shows that for this particular smile structure, the inhibition constant is something less than 0.2 nanomolar. Our job in this curation process is to standardize all of these as much as possible to make the model's job in predicting the Ki values from the smiles fairly straightforward. First, we will employ our function base smiles from smiles, which will allow us to take the smiles from our chemical database and remove possible salt groups or isotopes from the string, so we are just left with the base, ignoring these extra details that the model doesn't need. In this example, we're removing the sodium salt group and the isotope number on the chlorine. Next, we're going to use compute negative log response, which will allow us to turn the Ki's into pKi's. This helps in order to stabilize the variations in the data, in order to help the model more accurately find the trends in the data, and in this process of computing the negative log, we're also going to need to invert the comparison operators, since, for example, if the Ki for CCOCl is greater than 5e negative 7 molar, then the negative log of its Ki is less than the negative log of 5e negative 7. In this step, we're also going to convert our Ki's based on the unit it is given in, so that all pKi's are based on Ki in molar, not nanomolar or micromolar. Next, we're going to utilize the function standardize relations. You may have noticed that some of the relations in this table have quotation marks around them, and in the case of our last 2 examples with comparison operators, we note that a greater than sign means the same thing as a greater than or equal to sign. So we can standardize all of these signs into one form. As with any dataset, there are always outliers that must be removed, and so to address this, we employ remove outlier replicates, which is going to identify any compounds in the dataset that has multiple entries, and if they do, it ensures that they are removed from the dataset. In our case, the pKi of 1.505 is drastically different than the other replicates, and thus will get kicked out of our dataset. Lastly, we use aggregate assay data to combine those replicates that remained into one value using averages or maximum likelihood functions for those with comparison operators. Look at this final curated data compared to the raw data that we started with. We have standardized each of the columns of the data and combined duplicate chemicals. Let's take a deeper look at each of these steps by visiting the code. The first step we will do is to import the basic libraries that we're going to use in this tutorial: OS, Pandas, and NumPy. Once we've imported each of those, we can read in our data from the CSV that it was given in and convert it into a Pandas data frame. We can check the shape of the data frame in order to find that the dataset is comprised of 2,236 rows and 6 columns. Rawdf.columns.values gives us a list of each of the names of the columns. We've seen 4 of the 6 of these before, but we also know molecule Chembl ID, which is the identification number used in the Chembl database, and then standard type, which specifies the type of measurement that we're looking at, in this case, inhibition constants, Ki again. Now we can start running our data cleaning methods. We start with base smiles from smiles to remove those salt groups and isotopes and just get the base smiles we want. After importing the function, we run it by just inputting a smiles column as a list and assigning it to a new column in the data frame called base rdkit smiles. Note that we also specified a number of threads called workers to help accelerate the speed of the function. Looking at the number of unique entries in both the original smile strings and those in the new base smiles shows that we in fact succeeded in simplifying some of the smiles. Next, we will call compute negative log response. Our data spans across many orders of magnitude, which makes it difficult for a machine learning model to handle variances which change significantly with the magnitude of Ki. So this pKi will make for a more accurate model in general. After importing the function, we call it on our data frame, specifying the column that the units of each value are in, the column for the value, the name of the column that we want added with the new PKI values, the column with the relations, the unit string meanings for the unit conversion purposes, and an in-place parameter that specifies whether we want the changes to be made on the inputted data frame or just as an output to the function itself. We can then graph the original Ki and PKI values as histograms to see their distribution. As you've seen in our examples from earlier, sometimes databases have different formatting when it comes to relations. Some databases can have less than or equal to signs when others just have a less than sign, and some databases leave the relations column empty to mean the same thing as an equal sign. We call this standardized relations function to make all the relations format the same way. The parameters we pass in include our data frame, the name of the old relation column, and the name of the new column that we want the corrected relations to be put in. You may notice that we also name the chemical database that we are using under the DB parameter to help the function apply database-specific formatting changes. By looking at the counts of each type of relation in the old and new columns, we can see that we successfully standardized many of them. At this point, we have standardized the smiles, standardized the units, converted the Ki into PKI, and standardized the relations. All that's left in the data curation process is to use our last two functions to deal with any chemical structures that may have multiple values in our database. Our first function is remove outlier replicates, which will take in our data frame, the column with the chemical IDs, the response column, and the max difference threshold. The threshold is the maximum difference that we will allow a PKI value to be from the median of all other PKIs listed for that chemical, before we decide it's an outlier and remove it from the list. We run this function and assign the output to a new data frame called curatedDF. Once we've removed our outliers, aggregate assay data will combine all the multiple values listed that we decided weren't outliers. Since this is the last step in our curation process, this function has us input all the relevant columns from our data frame, and then it'll output a data frame with only the core columns that we need for the rest of the process. The chemical ID, the smile strings, the relation, and the average PKI for that compound. This aggregate assay data has a lot of parameters, so I'll go through each one quickly. The first parameter is just the input data frame that we got from our remove outlier replicates. The value col is the column with our PKI values. The output value col is the name we want to assign the column in the final data frame with the average values. The ID col, smiles col, and relations col are their respective column names in the data frame. Label actives is a parameter that we can use to add a new column with true or false values, denoting if the compound is active based on the average PKI value. We use that parameter for classification machine learning models, but we'll ignore it for these tutorials. Lastly, verbose just asks us whether or not the function should be telling us what it's doing as it's working. We can then print the original data shape and the curated data shape to see that our final curated data has significantly less rows as we combine duplicate chemicals and many less columns as we reduce the noise of the data to just the key columns that our model will care about. Finally, we can save our progress by saving the curated dataset that we made to a CSV file, and that way it's all ready for tutorial 2 when we'll split up the dataset into validation and training sets. See you all in tutorial 2.